In this part 2 video, we look at how OpenShift containers use PowerStore Metro volumes for active-active, high available storage. We will start by logging into the Patient node, which acts as a secure entry point into our environment. We'll verify the access to the OpenShift cluster and confirm that the cluster is reachable and healthy. In this setup, the Kubernetes control plane is running the following API endpoint. After confirming access to the cluster, we will validate the cluster health by checking the nodes. We will verify node names, node status, node roles. Now, let us verify the CSI driver in the OpenShift cluster. The CSI driver is what allows OpenShift workloads to use PowerStore storage seamlessly and dynamically. When we check the PowerStore namespace, we can see that both the controller pods and the node daemons are running successfully. As part of the CSI deployment, we also provide a configuration file that lists the two PowerStore systems the cluster connects to. This allows every OpenShift node to communicate with both arrays, and this setup is what we call a uniform topology. Now, let's quickly take a look at the UI of both PowerStore systems that are part of our Metro Volume setup. The first system is the one with the management IP ending with .60. This is PowerStore System A. Next, we have the second system with management IP ending with in .70, which is PowerStore System B. These are the two arrays we referenced in CSA configuration file. Let's take a look at the storage class that we use for creating Metro volume based persistent volumes. This storage class is named PowerStore Metro and it uses PowerStore CSI provisioner to create volumes. In the parameters section, we specify the primary array ID. We set the replication mode to Metro. We also specify the remote system indicating which secondary array participates in the Metro pair. With this configuration, any PVC created using this storage class will automatically provision a PowerStore Metro volume across two arrays. We have a simple PostgreSQL deployment running in the Postgres namespace. It includes a PVC for database storage, a secret for credentials, and a service for access. PostgreSQL is deployed as a stateful set, which created the Postgres pod and it is running healthy. Let us inspect the PVC's live manifest. Here we can see the volume that was created and attached to the PostgreSQL pod. Let's remember the name of the volume for now. It is ending with B855. Since this PVC uses the Metro storage class, the volume is created as a PowerStore Metro volume, which means it exists on both PowerStore systems. The one with management IP ending with .60, we can see the Metro volume and its attributes. And on the second array with IP ending .70, we see the exact same volume synchronously replicated and fully in sync. Let's check where the Postgres pod is running. From the wide output, we can see that Postgres is scheduled on node BM01. Now we know that the node, we log into the BM01 to verify the volume attachment. Now we are in BM01 node. From the LSBLK output, we can see multiple ISCSI paths for both PowerStore arrays, SDB, SDC, SDD, SDE. All of these paths are combined into a single multi-path device MPathD, and it's mounted to the PostgreSQL pod's volume path. In the multi-path listing, we can see multiple active ISCSI paths grouped under the same device, MPathD. Each path has a priority value, and multipath automatically uses highest priority path as a preferred route for I/O. All the paths share the same UUID, which uniquely identifies the metro volume across both PowerStore arrays. Here in the ISCSI session output, we can see 4 active sessions established from this node, 2 from PowerStore System A, 2 from PowerStore System B. In this test, we validate how the workload behaves when the primary storage path fails. I have loaded the pgbench data and now I am running 10-minute test. At the 5-minute mark, I'll disconnect the network to PowerStore System A to simulate a primary path failure. In the node 01, that is BM01, so before running the test, we check the multipath status. In the multipath status, all 4 ISCSI paths are active and mapped to MPathD, with the highest priority path being served, so which is from the primary system A. The test is running. Let's quickly check the PowerStore metrics to see live I/O activity. Now, when we check the metrics on PowerStore System A, we can see active I/O being recorded. This is because the workload is currently using the metro volume paths from system A, which have the highest priority. If we look at PowerStore system B, we don't see any IO activity at this moment. That's expected because the host is actively consuming the volume from system A due to the highest priority paths. The test started at 7:30 and it has now been running for 5 minutes. At this point, I'll disconnect the network to PowerStore system A to simulate the primary path failure. Now, at 7:35, I have disconnected the network to PowerStore system A. As soon as the active path drops, there is a brief freeze, which is expected while multipath detects the change. Now, when we check the multipath status on BM01 node, right after that momentary pass, multipath marks the paths to system A as a faulty and automatically redirects all traffic to system B. The Postgres pod stays healthy, the system volume remains mounted, and I/O continues without interruption. Now that the failover has occurred, let's check the PowerStore metrics again. On PowerStore system A, we now see no I/O activity, which is expected because the paths to system A were disconnected. If we look at the PowerStore system B, we can now see the activity I/O being recorded. This confirms that all traffic has successfully shifted to system B and the metro volume is being served entirely from remaining active paths. At 7:40, the 10-minute test finished successfully and there were no transaction failures recorded. Now, let's take a look at overall metrics to review how the system behaved throughout the test. OpenShift shows stable CPU throughout the run, and both the network and storage metrics remain healthy. After that momentary freeze, network bandwidth and packet rates stay steady with no packet drops, and storage layer continues operating normally through the transaction. Overall, this test confirms that PowerStore Metro Volume provides high availability. When the paths to one systems are disconnected, the host automatically redirects I/O to the other system, keeping the application fully available. The combination of Metro Volume, ALUA multipathing, and CSI integration ensures resilient and reliable storage access for critical workloads running on OpenShift. In this test, we validate how the workload behaves when the primary storage paths are restored. I have started the 10-minute PGBench test again, and at the 5-minute mark, I'll restore connectivity to storage system A to begin the failback. In BM01 node, before the failback, we check the multipath status. All active I/O is currently flowing through the paths to system B because system A was unavailable. The test is running. Let's quickly review the PowerStore metrics to see live I/O activity. Now, when we check the metrics on PowerStore system A, we don't see any I/O activity. This is expected because before failback, the workload was running entirely on system B. If we look at PowerStore system B, we can see active I/O being recorded. That's because the host is currently consuming the metro volume from system B as system A is unavailable. The test now at the 5-minute point, I am restoring the network connection to PowerStore system A. Now at 7:51, we simulate the failback event by reconnecting the network to PowerStore system A. As soon as the paths come back, multipath detects them immediately. This time, there is no freeze because new requests naturally shift to the preferred paths while any in-flight I/O continues on the existing ones. This transaction is seamless. Next, when we check the multipath status on BM01 node, we can see that the paths to system A are now active again and marked with highest priority. I/O has switched back automatically and system B paths have returned to standby. Now let's check the PowerStore metrics after failback. On system A, we can now see active I/O being recorded again, while on system B, I/O drops to zero. This is expected because system A has resumed its preferred role. At the end of 10-minute test, there are no transaction failures recorded. The workload continues normally throughout the failback event. In OpenShift console, on the left, we have the failure graph, and on the right, we have failback graph. You can see that during failback, OpenShift continues to show steady CPU usage and both the network and storage metrics remains healthy, very similar to what observed during failover. However, unlike failover, where a brief pause is expected as path switch, the failback path restoration is completely seamless. New IO immediately moves back to the preferred paths on system A, while in-flight requests continue on existing paths with no interruptions. This side-by-side comparison clearly shows that PowerStore Metro Volume not only handles path failures gracefully, but also restores preferred paths cleanly during failback, keeping the application fully available end-to-end. Overall, this test confirms that PowerStore Metro Volume restores preferred paths smoothly. Multipath automatically reroutes I/O back to System A without disruption, and the PostgreSQL application remains fully available. Metro volume, ALUA, multipathing, and CSA integration together ensure seamless storage connectivity even during failback operations. In this test, we validate how the application behaves when the worker node hosting the PostgreSQL pod fails. We want to confirm that the OpenShift automatically reschedules the pod to a healthy node and that the Dell CSM resiliency model ensures the persistent volume is detached from the failed node and reattached cleanly to the new node. Before simulating the failure, let's verify the current state of the PostgreSQL workload. We can see that the Postgres 0 pod is running on BM03 node. Now, let's check the pod labels. This particular pod label confirming that the resiliency model is active for this volume. When we inspect the PVC, we can see that it is bound to the Metro volume CSI wall, ending with B855 with a capacity of 500 GB, which is using the PowerStore Metro storage class. Let's also take a look at the PowerStore UI to verify host mappings for the Metro volume. First, I will check PowerStore System A. Here in the UI, we can see that Metro volume mapped to the host BM03. Next, I will switch over to PowerStore System B. Here as well, we can see that the same Metro volume is mapped to BM03 node. I will log into PostgreSQL pod and run a simple query to verify that the database is responsive. The timestamp query returns correctly, confirming that PostgreSQL is running normally before the failure. Now the test begins. I'm watching the pod in real time. We simulate a node failure by shutting down BM03 worker node where the pod is hosted. The virtual pod begins to terminate. This is expected when the node becomes unavailable. Shortly after termination, a new instance of the same pod, Postgres 0, goes into pending state. Then it moves to container creating as OpenShift schedules it onto a healthy node. Within seconds, the pod transitions to running again. This confirms that the resiliency module and CSI driver successfully detached the volume from the failed node and reattached it to the new node. When we check the cluster again, we can see that the new Postgres 0 pod is running on BM02 node with the new IP. Now I will log into PostgreSQL pod again and run the same timestamp query to verify that the database is responsive. The query returns successfully, confirming that the PostgreSQL is running normally after the pod has moved to the new node. After the pod moves to BM02, let's check the PowerStore UI again. On PowerStore System A, we now see the Metro volume mapped to BM02, the new node hosting the pod. On PowerStore System B, the same volume is also mapped to BM02. This test confirms that when the worker node hosting any applications becomes unavailable, OpenShift and the Dell CSM resiliency model respond automatically. The pod is rescheduled to a healthy node and the persistent volume is cleanly reattached and the applications comes back online without data loss.